any moment further, I think we shall begin with the session. Over to you, sir.
Okay, thank you, Aditya. Yeah, I'm sharing my screen. Is it visible?
Yes, sir, absolutely.
Okay. So again, welcome to the SCTP under the aegis of Global Initiative of Academic Network GAN. This is the third session of second day, and today we'll go for the calculation of the seismic forces using the Indian code for earthquake resistant design. In the last lecture, we said that the earthquake, maximum loss of life and economic loss is associated, and our philosophy is saying that the damage is allowed, but collapse is not allowed. To achieve the aims of our philosophy, we always say that we cannot predict earthquake or stop earthquake event to happen, but we can prevent collapse of structures by adopting good technology and good practice. So here we are talking about the good practice, and so before we start the session, means we go for the methods which are given in the Indian standard. We talk about some basics of dynamics of single degree of freedom system. We are knowing that if we consider a single story building and it is subjected to earthquake. Now we are knowing that the earthquake is applying the displacement at the foundation level. Now, when the displacements are applied at the foundation level, at that moment, this building will experience inertia. If you look at the Newton's first law of motion, it said that a body at rest will try to remain at rest, and body in motion, it will continue its motion unless and until some external force will act on it. So what will happen when earthquake shaking starts? At that moment, our building, basically it is at rest and it will try to remain at rest. So the masses which are present in the building will exhibit the inertia, and because of that, the inertia force will induce in the system, and this inertia force is produced because of the earthquake. It is known as earthquake force. So earthquake force is nothing but it is the inertia force. It is mass time acceleration. So our building will behave like an inverted pendulum. So what we assume here, we assume that the mass is concentrated. Mass is concentrated at the floor level. We are knowing that mass is present everywhere, and if we consider mass is present everywhere, it means the inertia force will produce everywhere. And if we consider like that, then we have an infinite degree of freedom. And if we have infinite degree of freedom, then our matrix will be of infinite by infinite. And basically, we do not want to involve ourselves into too much mathematics, and therefore what we are doing, we are assuming something. And what we are assuming that mass is concentrated at the floor level, because there is a slab, and this slab is having a very heavy mass at one particular level when we are talking about the lateral displacement. So we assume that the mass is concentrated at the floor level or the slab level, and we converted our system, which is having the infinite degree of freedom system, into a single degree of freedom system, and so it behaves like an inverted pendulum. This is what we assume. And when we talk about this, then the most important term we must know is the natural frequency, right? So we are knowing the natural frequency. that is the omega is equal to square root of k by m, or you can say this is the circular frequency we have. If we talk about the natural frequency in terms of cycle per second, then it will be omega is natural frequency is equal to 1 upon 2 by square root of k by m, right? So here this frequency depends on k and m, these two property. K is the stiffness of the system and m is the mass, right? So this is very important for us. And you see, when earthquake occurs, then when we ask the question, which building will be affected more? Now at that moment, we have to answer in such a way that it should be correct from all aspects. For example, if I'm saying low-rise building will be affected, now if low-rise building will be affected, then I'm wrong. If I'm saying high-rise building will be affected, I'm wrong, right? What is the reason? The reason is when we are talking about a building is having its own frequency. Building is having its own frequency, right? Now, when I'm talking about a low-rise building, then in case of a low-rise frequency, the stiffness is very high. If the stiffness is very high, then the natural frequency will be high, right? So, what we can conclude that low-rise building is having high frequency, and high-rise building, the high-rise building is having low frequency. Right. Now, we are knowing the another phenomena, that is the resonance. The resonance means the frequency of a system matches with the external frequency of external excitation force. Now, if these two matches, then the system will exhibit very large response, right? Or larger displacement will be observed. So here, suppose a low frequency earthquake will come. Now, if the low frequency earthquake will come, we are knowing that the high-rise building having low frequency. If high-rise is having low frequency, then this low-rise building will affect the high-rise building rather than a low-rise building. Suppose if I assume it is a high frequency earthquake, or the earthquake contains high frequency, right? If earthquake contains high frequency, then the low-rise building will be affected, right? So we have to give a logical answer, right? So we cannot say a high-rise building will be affected or low-rise building affected. It depends on type of earthquake which is going to be there in the region, right? So when we are talking about a vibration, right, then we have three possible types of deformed shape, right? It depends on the stiffness of the system. For example, the first one I'm showing is this is the flexural mode, right? When the stiffness is less, then your system is very flexible, and is flexible, then it will exhibit this flexural type. If it is stiff, then it will be of a shear type. And if this is some intermediate case we are considering between the flexure and the shear, but generally it is either a flexural deformation, shear deformation, or combination of flexure and shear. And when we are calculating the earthquake force, we are knowing what is the earthquake force. The earthquake force is the mass into acceleration. F is equal to ma. This is the Newton's second law, right? Mass into acceleration, that is the Newton's second law. So what we are doing here, we are doing the same thing. We are knowing that there is a heavy mass located at this particular level, and when the shaking taken place, this mass will vibrate with certain acceleration. And when it vibrates with the acceleration, then this mass into acceleration, that is the inertia force, which is produced at the floor level, right? So that is known as the earthquake force. Or the another way to find out the earthquake force is we are knowing the stiffness and we are knowing the displacement of the mass. Then the stiffness multiplied by the displacement, that will give you the force induced in the system, right? So this is known as a design earthquake force. Right. Now, sometimes the system is having a higher degree of freedom also, right? So in this case, you can see here the masses are located at different level, this level, at this level, at this level, right? So here we can say this is the 4 degree of freedom system. Or if you are talking about the large fluid tank, then the mass is located here, somewhere here. So we can have a multi-degree of freedom system. Means degree of freedom is higher than 1. Right. So I'm taking a very simple thing. You see, when we go for the code-based procedure, we must have certain idea of the mode shape. The mode shape is nothing but it is a deformed shape of the structure, right? Because your structure is vibrating, and uh, the applied frequency, it depends on the applied frequency, because your system is having its own frequency, right? Now what is the applied frequency? uh, on the basis of that applied frequency, your system is going to vibrate, right? So here what I'm saying is, like, if the mode shape is a deformed shape, so here it is a 3 degree of freedom system. So I'm going for uh, the spring mass model or the stick model. Now I'm saying this is the mass m1, m2, right? These are the lumped masses at the floor level. This is our assumption, remember, right? We don't want to make our calculation complicated, right? So now when we are going for the 3 masses at that moment, uh, when we go for the mode shapes, then uh, for different frequency, your system is going to vibrate in a different way, right? So when we're talking about the single degree of freedom system, we have a we have a single frequency, right? And when we are talking about the 3 degree of freedom system, we have 3 frequencies, and corresponding to these 3 frequencies, we have 3 different deformed shapes, right? So it is known as a mode 1, mode 2, mode 3, right? So we have a 3 different mode shapes, right? And then what we do, then we again, it is having a 3 degree of freedom. So we are creating mass matrix, stiffness matrix, right? And this matrix will be of 3 by 3, right? And then we try to solve it, right? Now it is basically an eigenvalue problem, right? So this is the mode 1, right? Your system is vibrating in the mode 1. It may vibrate into mode 2, mode 3, right? So basically it is a 3 degree of freedom system. So we have a 3 dominating frequencies, and on that basis we have a 3 mode shapes. And most of the time, uh, what we are doing, like, there are 3 masses, but we are converting these 3 masses into a single mass, and we are converting stiffness into equivalent stiffness, right? So this 3 degree of freedom system can be represented by a single degree of freedom system also, right? So this can be done very easily, right? So if we talk about the 3 degree of freedom system, and when we plot a response curve, acceleration versus the frequency, right? If we plot this curve, then we are knowing that it's a 3 degree of freedom system. So we must have 3 peaks, right? So this is the peak number 1. This is the mode. This is the response corresponding to mode 1. This is corresponding to mode 2, corresponding to mode 3. Now question will arise, in which mode your system is going to respond more, right? So it depends. Again, it depends, because if for example, if I'm saying my structure is having 3 frequencies, for example 3 hertz, 10 hertz, and 20 hertz, for example, right? 3 hertz, 10 hertz, and 20 hertz. Now if earthquake which comes, it contains the 10 hertz frequency, then the response in the second mode will be higher. If earthquake contains 20 hertz frequency, then the response in the third mode will be higher. If frequency is lower, then it may vibrate in the first mode, right? It depends. So we have to check whether in which mode we will get the higher response, right? So mode 1, mode 2, or mode 3 in case of a 3 degree of freedom system, right? And we can also superimpose these modes that we'll learn later on, because during the vibration we have to consider a maximum mass which is supposed to be participated, and if it will participate, then and then enough inertia is created, and then we will very close to the correct solution, right? So we'll do that. And you see, this is a very simple example. It's a 3 degree of freedom system, and masses are given, storage stiffness are given. So this is, you see, I'm just brushing up this knowledge, and we have to calculate the frequency, right? So we have to go for the eigenvalue problem. So this is the equation, k minus omega square m, and from this we can have these 3 frequencies, right? 3 frequencies, and these are the 3 natural period, natural frequency, and the time period, or you can say natural period. So the lowest frequency is known as the fundamental frequency, right? So omega 1 is the fundamental frequency, omega 2, omega 3. So it's a 3 degree of freedom system. We have a 3 dominating frequencies and corresponding natural period. So we are knowing that the natural frequency is equal to 1 upon 2 pi square root of k by m, right? This is the equation of natural frequency, right? Now this is nothing but this is the inverse of what? This is the inverse of natural period, right? So the natural frequency is, you can define as numbers of cycles of vibration per unit time. And what is the natural period? The natural period is time required to complete one cycle of vibration, right? So they are inverse of each other. So if your building is having a lower frequency, then it's having a higher natural period. So the omega 1 is 17.16, it's a lower than 47. So the natural period, it will definitely be higher, 0.36. T2 is a 0.31. So these are the natural period of the system, right? So we have to go for the mode shapes, and these are the, so we are plotting the mode shapes. It's very simple. It's k minus omega square m phi. Now this phi is nothing but it's a mode shape. We have to find out this mode shape corresponding to mode 1, 2, and 3, right? So these are the mode shapes we derive from this, and this is for the mode 1, this is for the mode 1, this is for the mode 2, this is for the mode 3, and when we plot, we get this type of mode shapes, right? So these are the fundamentals. Just we are clearing, right? Now the structure analysis procedures that we follow, right? So we are following different methods, right, for the analysis. It may be an equivalent static method, response spectrum method, push or time history analysis, right? Now these different methods, basically it's categorized on the basis of which type of nature of analysis they are considering, right? For example, dynamic means loads are change with the time, right? And non-linear means the the system is loaded beyond the elastic limit, right? So when I'm talking about the equivalent static method, then basically we are not considering any non-linearity. No, we are not considering any non-linearity. So it is a linear, and at the same time it is a static. So we are not considering any dynamic thing in the calculation. So it is a linear static, right? So name is given equivalent static, no dynamic effect, no material non-linearity. When we're talking about the linear dynamic, the response spectrum method comes under that category. Now linear means we are not talking about any non-linearity, but dynamic means we are talking about the loads which are changes with the time, right? So dynamic effect we are considering in the response spectra. The nonlinear static, the Pushow analysis is the case of nonlinear static, right? Where dynamic effect is not considered, but we are pushing the system in such a way that it enter into the nonlinear range, right? So material nonlinearity is considered. And the time history analysis. The time history analysis is in a real sense is a nonlinear dynamic. Means here we are talking about the dynamic nature of the load. At the same time, we are also considering the non-linearity of the material. Both the things we are considering, and therefore this analysis is considered to be the best among all the analysis, right? But lot of mathematics is involved in this case, right? Lot of mathematics is involved in nonlinear dynamic analysis. Now just imagine if you are talking about any structure and you have degrees of freedom more than 3000 degrees of freedom. Now when it's a 3000 degree of freedom system, your matrix size will be 3000 by 3000, and it is very difficult to analyze, right? So time history analysis is giving you a better result as compared to other, but it is very time consuming, right? So therefore we are going for the certain simpler methods, and which are very fast, and it is very easy to digest by the most of the people, right? So the linear static, like equivalent static analysis we are going, then it will be a very fast and very easy method, right? But at the same time, if you follow dynamic analysis, if you follow the static analysis, then there is a difference. When we are going for the static analysis, it is always conservative. It is conservative in a way that it will give you the result on the higher side most of the time, and therefore uh, it will become uneconomical. So if you are good enough in the dynamic analysis, definitely you have to go for the nonlinear dynamic analysis is better, definitely. But again, time is the constraint, and for the simplicity we are going for the very simple approach. So how can you select this procedure? It depends on the seismic design category, right? Now which type of the structure you are designing, right? If you are designing a very important structure, then definitely you have to go for it. Suppose if I'm going for the important structures, then I'm always going to go for the dynamic analysis. Performance level means we have a different performance level. We have a life safety, immediate occupancy, collapse prevention, many different types of performance we are defining, and on that basis also we select these methods. Structural characteristics, whether your structure structure is regular or is complex, right? It depends. Suppose if your structure is irregular, in that case definitely the dynamic analysis is preferred. The response characteristics, like sometimes if you're talking about the tall structures, in case of tall structures the higher mode may contribute. In that case also the dynamic analysis is preferable. Availability of data and the confidence limits for the performance level, right? So these are the some. So now we come to the main part, that is the seismic code, IS 1893. The IS 1893 it gives you the criteria for just a moment. Just one moment. Okay. IS 1893 is a criteria for earthquake resistant design of structures. Right. We have a sixth revision. So in the fifth revision, already this code is divided into the 5 parts. Earlier there was a single code, and in 2002 when it was revised, it was divided into 5 parts, and in 2016 the last revision what we have of part 1 in 2016. All right. So the part 1 is general provision and building, part 2 is the liquid retaining tanks, part 3 is bridges and retaining walls, then of part 4 is industrial structures including stack-like structures, and part 5 dams and embankments. So these are the 5 parts uh, of IS 1893, and today we are talking about the part 1. It's a general provision and building. The provisions, general provisions means it will be also useful, or you can refer to other codes also. And part 1 is generally made for the building, right? So general provision will be applied to other structures also. So what are the assumptions? When we go for the code is taking certain assumption. The first assumption is that earthquake causes the impulsive ground motion, which are complex and irregular in character, changing in period, amplitude, each lasts for a very small duration. Right? So it describes the earthquake event. Right? So earthquake is an impulsive ground motion. Right? It carries different frequencies. So when earthquake shaking taking place, at one moment you have a 3 hertz frequency, next moment you have 10 hertz frequency, then you have 20 hertz frequency. It depends. It keep on changing. The earthquake will not continue with a single frequency. Right? So the code is saying that the earthquake carries different frequencies. Now, when we are talking about our structures, the structure is having some definite frequency because we constructed our structure. Once construction is over, its stiffness is fixed, its mass is fixed. So if stiffness and mass is fixed, then the natural frequency, natural period of the constructed building is well defined, right? Now this earthquake comes with the different frequencies, right? It contains different frequencies. I told you that 3 hertz, then 10 hertz, and 20 hertz, right? So these frequencies are keep on changing during the shaking. So what is going to happen in that case? The resonance is not possible, right? Resonance is not possible. The reason is your building is having its own frequency, but the earthquake carries different frequencies. And you see, if you apply the same frequency continuously for a longer time, then resonance will be built up, right? Resonance will be built up. So in the first assumption is that the resonance is not possible most of the time as far as earthquakes are concerned. So code denies the resonance except one earthquake. The one earthquake was a Mexico City earthquake of 1984. Right. This Mexico City earthquake, it was a very low frequency earthquake, right? And during this earthquake, a lot of damage, lot of casualty was observed, right? And everyone was surprised. What happened? This Mexico City earthquake taken place in 1985. It was taken place 300 kilometers away from the Mexico City. It was a very low frequency earthquake, and because of this earthquake, almost 8 to 15 story buildings were either damaged or collapsed. Right. So everyone's surprised. What happened? Now they concluded that this earthquake contains almost it was a very low frequency earthquake, and throughout the shaking almost the frequency was not that much vary, right? It means it's a 3 hertz and 20 hertz, and no, it is not changing its frequency. It was a very low frequency earthquake, and the frequency content by the earthquake was almost in a very small or in a small or narrow range, right? Now, actually, what happened in that case? The very low frequency earthquake came and 8 to 15 story building affected. Uh, Now, question was because of this low frequency, this building should not affect, right? But they are affected, and when they study that earthquake, they find that this low frequency earthquake when reaches the Mexico City, the Mexico City was built. There was a lake earlier, and this lake was filled up, and then these buildings were constructed. So when this soft means this low frequency waves reaches to the this filled up soil, this filled up soil is soft in nature, and the soft soil is having the characteristic, it will magnify the earthquake ground motion, and this low frequency earthquake was magnified, and the frequency was increased, and this frequency matches with the frequency of 8 to 15 story building. So this is the only earthquake where earthquake engineers are not denying the resonance, but except that in the code it is assumed that resonance is not possible. The second assumption is earthquake is not likely to occur simultaneously with the wind or maximum flood or maximum sea waves, right? It is not going to occur because earthquake event is a very short duration event, and it is not going to occur at a time with the wind, flood, and sea waves. Sometimes in the serials, in the TV serials, they are saying when earthquake comes and also the wind is blowing. This is not going to happen in a real life, because earthquake event is either maybe a 2 minute or 3 minute event. That's all. And during that, in past we have not observed any such phenomena, right? Even we are saying the tsunami is going to take in place once is after a long time, and earthquake stops, and then this tsunami is going to hit it may take 30 minutes, maybe take 45 minutes. It depends to build up the response because of tsunami, right? And the value of elastic modulus of material uh, when we have to consider is considered as a static analysis, right? And this is defined. Now, what is the objective? The objective is to find out the design seismic force and its distribution at different level along the height of the structure. Because you see, we are knowing that our building is a single story, it may be a 3 story, it may be a 10 story, it may be a 20 story, right? It depends. So if it is a 20-story building, then it is very difficult to analyze by means of analysis methods. All right. So code has given some simple type of methods for the analysis, and we're going to discuss that part. So which data you want? You need a type of building, architectural drawing, the structural layout, location, soils data. These are some data which is required before you go for the analysis. So IS 193 part 1 2016 is saying that you can perform two types of analysis: the static coefficient method. You can use the dynamic analysis, and this dynamic analysis we have different types of methods: the response spectrum, modal analysis, time history analysis. But the code is actually have included the two methods: the response spectrum method and time history method, right? So we have two types of methods: static coefficient, you can say seismic coefficient method, and another is a dynamic analysis, is by the response spectrum method or time history method, right? So we'll first discuss the static coefficient method, right? This static coefficient method is used to determine the lateral force because of the earthquake. And you see, the name is a static coefficient method. It means the earthquake force, basically it is dynamic in nature, but we are applying in a static way, right? The way in which rate load is acting, the same way we are applying this load, right? So this is not the real condition the load is actually dynamic. Earthquake load is a dynamic load, but here we are applying in a static way, right? And why we are doing that? We are knowing that the many civil engineers are not knowing a dynamic analysis, right? And in that case, if we are not going to give any alternate, then it is very difficult for them to understand the behavior or to design the structure. So the alternate method has been given. This is a static load. It's a static coefficient method, in which you have to apply a little load like a static load, right? And you can analyze. So most of us are very comfortable with the static load, not comfortable with the dynamic load, right? So this uh, uh, the static coefficient method, it is also known as a first mode analysis, right? First mode analysis, right? So basically, we are not considering any mode at all. I tell you, dynamics is dynamics. If you refer the code, no dynamics is involved at all. But if you look at the logic behind the static coefficient method, then definitely it is a first mode analysis. We are not going for the second mode, third mode. We are not considering any other mode, right? Uh, so this first mode may be a linear or it may be a parabolic, and our code has assumed this is a parabolic distribution, right? Uh, Generally, for low to medium building, we have this type of deform shape we consider, then it is good. But if the structure is having a natural period more than 2 seconds, the deform shape is parabolic, and our code has taken this distribution as far as the static coefficient is concerned, right? So what we do, we calculate the base shear. The base shear is mass into acceleration, right? So we calculate the mass into acceleration, and this base shear is acting at the foundation level. It is at the base, right? And then this base shear, is divided into the story forces or lateral forces at the story level. This is F1, this is F2, right? Uh, this is F3, right? So what we do, we are simply distributing this force, right? So VB is equal to WHI square to WK HK square. So that will give you a forces at the story level, right? So distribution of the forces along the height. So what we are doing, we are simply performing the usual static elastic structure analysis, right? No dynamic analysis involved. I tell you, no dynamic analysis is done here. But this is the most important part. It is a hidden in concept of response spectrum used in assumed vertical distribution of the base shear, right? So this response spectrum is involved here, and it is basically the first mode which is considered, right? So this is what the equivalent lateral force method or static coefficient method, right? So how will we calculate the base shear? The base shear, we have an equation of the V is the base shear is equal to AH into W. The AH is a design horizontal acceleration. Right? So this base shear is a multiplication of AH into W, and this AH, the AH is comprised of this part, Z by 2, I by R, SA by G. Now, what is this Z by 2, I by R, SA by G? Basically, you see, you understand this part. This is actually this is the W, right? So we have certain coefficient AH here, AH, and what is this? Multiply by what? W means it is mass into acceleration, right? It is mass in the m into g, right? Now, if I am putting, instead of this W, if I'm putting m into g, then what is going to happen? This g will cancel out, this g will cancel out, this g and this g will cancel out. So it is m, mass into SA, means acceleration, mass into spectral acceleration. So that is the inertia force, and these are the some additional thing attached to it: z by 2, I by r, SA by g, right? So these are the additional thing attached to it. These are the coefficient. So it depends on different things, right? So it is z by 2, I by r, SA by g into W, right? The z depends on what? The z depends on what? The z is a zone factor, right? It is a zone factor. It In the last lecture I told you that India is divided into 4 seismic zones, right? It is divided into 4 seismic zones: zone 2, 3, 4, and 5. Earlier there were 5 zones in 1984 IS code. There are 5 zones, and these 5 zones are reduced to 4 zones. So zone 1 and 2 were merged in 2002. So now only 4 zones are there: zone 2, 3, 4, and 5, right? And we are knowing that zone 2 is having the least seismic risk and zone 5 is having the highest seismic risk, right? So this coefficient, the value of z, it depends on uh, 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 on the uh, different zones, right? And these zones, z is having a higher value for the zone 5 and lower value for the zone 2, right? Then we have I by r. I is the importance factor, r is the response reduction factor, SA by g is the spectral acceleration, is normalized with respect to gravitational acceleration. So if you look at this r value, the response reduction factor, basically it supports our design philosophy, right? And SA by g means the acceleration of the system, it depends on the structural characteristics, right? So we are knowing that shaking of the foundation taken place. So how much acceleration your structure is going to observe, it depends on the structural property. What is the stiffness of your structure? What is the mass of your structure? It depends on what is the damping of your structure. So this SA by G value will depend on the structural characteristics, maybe a stiffness, it depends on mass, it depends on damping, right? And this R, the design is a design philosophy. We'll discuss that part, right? So basically, these are the parameters: importance factor, zone factor, time period, response reduction factor, damping, seismic weight, on which this base shear depends on, right? Now, we'll discuss the first part, the seismic weight. Now, as per the IS 1893, clause number 7.4.1, the seismic weight is basically dead load plus or minus is a plus appropriate live load, appropriate imposed load, right? Appropriate imposed load. Now we are not knowing what is the appropriate imposed load, right? So dead load plus appropriate is the appropriate imposed load, right? It is imposed load. Now we are considering the full dead load. Remember, we consider the full dead load, but we are considering a, appropriate imposed load. Why? What is the reason? And if you refer that clause number 7.3.1, it is mentioned that up to the 3 km square impose uniformly distributed floor loads, then consider how much load you have to consider. Percentage imposed load 25%. And if the live load is more than 3 km square, then you can consider 50% load, right? It means here dead load plus 0.25 imposed load or 0.5 imposed load, right? This is going to be there, right? Now what is the reason behind it? Why we are considering the reduced live load? Why we are considering reduced live load? Can anybody explain this? Why we are talking about the reduced live load or reduced imposed load? We are not considering the full imposed load or full live load. What is the reason? Anyone can explain? Yes? Anyone? Can you answer this? Why we are considering the reduced imposed load or reduced live load? Why we are not taking full live load or full imposed load? Anyone?
Hello.
Yes.
It is not necessary that at the time of earthquake full live load will be present. This is one reason. And second thing is it is many times live load will not impose inertia forces because it will start vibrating. These are the two reasons which are given.
Yes. That is the correct answer, and the correct answer is like you see when we're talking about the live load, like we talk about the load of the human beings or the load of the furniture, right? Now during the shaking, what is going to happen? This furniture and is not attached with the floor. So what is going to happen? It will slide, right? So there is a friction between the for example furniture and the floor. Now this friction, we assume it is a maximum value is 0.5, right? And therefore what is happening, when it shakes, then the inertial force of that furniture is not going to transfer to the floor, and therefore we are taking reduced live load, right? So that is the reason we are considering the 50% or 25%. It depends on the intensity of the live load, right? Then the value of this, we are knowing that this zone factor is 1 minute. Yeah. Here I told you that this is the seismic zones of India. The India is divided into the four zones: zone 2, 3, 4, and 5. Right. So if I'm saying the Ahmedabad is in zone 3. So we have to consider some different value, right? The same way, if I'm talking about the Bhuj is in Kutch or Bhuj, that is in zone 5. If I'm talking about the northeast states like Mizoram, Manipur, Nagaland, they are in zone 5, right? This red part is saying the zone 5. This red part is zone 5, right? This is zone 5. So we have to take the this value of zone 5. Same way, this green part, what you're observing is zone 4, right? This yellow part is zone 3, and blue is zone 2, right? So here the code has given the different value, right? For the zone 2, the Z value is 0.1. So it depends on the intensity of shaking, I tell you, right? Seismic zone factor zone 3, 0.16, zone 4, 0.24, 0.36. Now, if you look at this almost a 1.5 tower. This is the first is 0.1 multiplied by 1.6, then 0.16 multiplied by 1.5, then 0.24 multiplied by 1 multiplied by 1.5, it is 0.36, right? So this zone 5 is having the highest value of the Z, and 2 is having the least value. So if you look at this, the Z is in the numerator. So if you are saying the two identical buildings are located, one in zone 2 and another is in zone 5, right? Both the buildings are same, but even though when you design, then you have to design for 3.6 times higher force if your building is located in zone 5 as compared to building located in zone 2, right? So 3.6 times. So this we have to understand that we have to design our building for the higher earthquake force. And here the another important thing, there's a Z by 2. Now why 2 is introduced here, right? Why is 2 is there? Because the maximum credible earthquake is reduced to a design basis earthquake, and that is the reason it was done, right? And this zonation is done on the basis of the intensity. So yesterday we have discussed that Ahmedabad is in zone 3. So the intensity of shaking what we felt in the 2001 earthquake was the 7, right? It was 7. So it was not exceeded beyond our expectation, right? So it was not an unusual earthquake. It was a routine earthquake, but our construction was poor, our structural design was poor. That's why we have seen the tremendous devastation. If it is zone 5, for example, then the intensity of 9 and above is expected. If it is zone 4, the intensity 8 is maximum intensity 8 is expected. If it exceeds this limit, then we can say it is an unusual earthquake, right? But most of the time we haven't seen such things, except Latur, for example. When in case of a Latur earthquake of 1993, the Latur was in zone 1, and the intensity of shaking what was felt was of zone 3, right? So here, this is the seismic zone of India. Now the second, the second factor, there's I, Z by 2, then I by R, right? I. What is I? I is the importance factor. This importance factor depends on functional use of the structure, the hazard level, if structure fails, the post-earthquake functional need, historical value, economical importance. For example, we talk about the hospital building. Now, hospital is important for us as far as the post-earthquake need is concerned, right? Your hospital building should remain functional after earthquake, right? And therefore, we have to design this hospital building in such a way that it should not it should remain functional after earthquake. It means we designing for the higher earthquake force. For example, we are talking about the historical value. We have a heritage structure, and like Taj Mahal. When we talk about Taj Mahal, then definitely we are not designing for the 50 years or 100 years. We are designing or that was designed maybe for the more than 1,000 years, right? It may remain functional. So it depends. Suppose if we are creating a heritage structure or historical structures, then definitely we have to design for the higher value as far as the earthquake force is concerned. Functional use, for example, TV towers and many other important like railway stations. This should remain functional after the earthquake. So therefore, this importance factor, it is given in this way. And important services and community buildings, monumental structures, emergency buildings like telephone exchange, television stations, radio stations, railway stations, fire stations, cinema hall, assembly hall, power stations, subway stations. The I value is 1.5. 1.5. And for all other building, it is 1, right? Now, as per the old code, only these two categories were there, but in 2016, this was introduced. It is if occupancy is more than 200, right, in a building, It may be a commercial building, it may be a residential building. If it is the occupancy is more than 200%, then we are knowing that if this building will collapse, then a lot of casualty will happen, and therefore we are designing this building for the higher earthquake force. So 20% increase is observed as compared to a normal building, right? And the important building like hospital buildings and this the community buildings, monumental structures are designed for 1.5 times, means 50% higher force, right? You are knowing that the hospital building was collapsed in Bhuj, right? Hospital building collapsed in Bhuj, and it was a very pathetic situation. I tell you, we reached there 2 days after the earthquake taken place, and we have seen that people are taking treatment in the open, right? So this is really pathetic, I tell you. So all important buildings should remain functional because it is required. Right? The next one is response reduction factor. Again, we have discussed Z. Z is a zone factor. I is the importance factor, and now the next one is the R. R is the response reduction factor. Right. So here this R is in the denominator, right? R is in denominator. So higher value of the R is considered better. Higher value of R is considered better, right? Because then base shear will reduce. So it depends on performance. Now, which are the factors on which response reduction factor depends? Now, this is very important. So this response reduction factor depends on these three the important characteristics: ductility, overstrength, and redundancy. Right? Now, you see, as per our design philosophy, we are knowing that our structure will observe damage, but it will not collapse. We are making our structure to enter into inelastic zone, right? So our structure is entering into inelastic zone. So what is ductility? Ductility is the capacity to undergo large inelastic deformation after yielding without losing strength and stiffness, right? So once your structure is moving out of the elastic range, it enters into the inelastic range, and how much it will deform after yielding, it is nothing but it's a ductility, right? Ductility, also I'm saying that ductility and damage both are related. Ductility means what? It's a capacity to undergo large inelastic deformation. Inelastic deformation means permanent deformation, right? So ductility makes your structure enter into the inelastic range. So definitely a permanent damage will be there, right? So damage is associated with the ductility. This is one. So this R factor, basically I told you earlier that, you see, this is very important. This is the R factor which basically supports our philosophy. It supports our philosophy, right? Ductility. Your structure should be ductile. The earthquake release the energy, and your structure has to absorb this energy, right? So this is the way we are designing. So again, I'm saying earthquake resistant design is not a strength based design. Earthquake resistant design is a based on energy absorption capacity of a structure, right? So ductility is a very important part of it. Because the second part is the overstrength, and third is the redundancy, right? Now this is very important, right? You can see this. Yesterday we have discussed that this is the maximum force, right, which is acting on your structure. This is the maximum earthquake force. We are not designing for this force, I tell you. We are not designing for this force. We are designing for this force, right? It is a fractional load, I tell you. This is 100 kilonewton. Then we are designing for maybe a 15 kilonewton or 20 kilonewton, right? No factor of safety. right? We are not applying any factor of safety here. We are designing for maybe 20% force, 25% force, it depends, right? So actually this is the design load, right? And why we are choosing this? Because we rely highly on the ductility, we rely on redundancy, we rely on overstrength, right? What do you mean by redundancy? Redundancy means, suppose if I'm giving you a very simple example, if you have a table having 4 legs, right, then if any one leg of the table is get damaged, then your table will become unstable, right? But suppose instead of that, suppose your there are 4 legs required for the table to remain stable, and I'm adding 2 more legs, right? So actually 4 legs are required for the equilibrium, and I'm adding 2 more, means that will provide a redundancy. So such kind of redundancy we have in the real structure. I tell you, in buildings we have a higher degree of redundancy. But if I'm talking about the bridges don't have a higher redundancy. Suppose it is a simply supported uh, bridge, right, or simply supported deck. In that case, if that uh, deck will fail, right, then uh, or any pier will fail, then your bridge will fail. So redundancy is almost zero in case of bridges, but we have enough redundancy in case of buildings. Overstrength means what? You see, uh, I'm giving you a very simple example. For example, uh, we use the concrete. Suppose we use the M25 concrete on site. Now this M25 concrete is supposed to be designed in the laboratory, right? So when it comes to the mixed design in laboratory, then we are not designing for 25. We are adding some standard deviation, and we are, instead of 25, we are saying that we design the same thing for uh, uh, with the standard deviation be 30, 32, right? So we are knowing that on site that quality control is not achieved, and therefore we are in laboratory it is achieved. So we design for 32 in the laboratory, and or 31, then it will give you at least 25 on site under the condition where quality may not be achieved thoroughly, right? So just imagine, instead of 25, suppose a good quality control on the site, instead of 25 your concrete is having the strength of 28, 29, then it is giving you the overstrength part. Or you can say uh, uh, so many overstrength factors we have, right? So this ductility depends on this 3 part, right? And basically if your structure is able to undergo large deformation, then it is considered to be ductile and it is able to absorb more energy, right? Now as per the is code has given different values of R, right? For example, moment frame systems. First is a RC building with the ordinary moment resisting frame, OMRF, right? OMRF means ordinary moment resisting frame. The R value is 3. Now OMRF means we are going for IS 456 detailing. I tell you, IS 456. This code is followed here, but the code of ductile detailing is not followed, and therefore the value is 3. But in this SMRF is a special moment resisting frame where 456 plus you have 13920 detailing, right? 13920. This detailing is there, and so 456 plus 13920 detailing is considered to be a special moment resisting frame. Now value is 5. Now just look at this. It is 1/3, right? 1/3, and another is 1/5, right? It is actually R is in the denominator, right? So what is this? Basically, this is 0.33. right? 0.33. This is 0.33 and this is 0.2. This is 0.2, right? And it is almost 65% increase in the load. You see, code has given direct penalty, right? If you go for the, if you are following IS 13920, it is good, right? And if you don't follow, then you design your system for the 65% higher load, right? Same way, steel building with the OMRF 3, steel building with this SMRF is 5. Same way in a brace frame also. But here we are interested in the load bearing masonry structures, right? Because this is a confined masonry program, so we have to look at this load bearing masonry structures. So we have to look at this unreinforced masonry without horizontal RC band, right? Designed as per IS 1905. It is 1.5, right? No seismic bands, right? 1.5, because the performance is poor. Unreinforced masonry with a horizontal RC seismic band. If a horizontal band is there, it will become 2. Unreinforced masonry designed as per with horizontal RC band and the vertical reinforcing bars. So definitely the band plus vertical reinforcing bar performance is improved. Reinforced masonry, it is good, 3. And confined masonry, here comes this confined masonry, and the value is 3. So as far as the masonry structures are concerned, this confined masonry is having the highest value of R, right? So suppose if you are designing unreinforced masonry, right, without bands, then and you are designing a confined masonry, right, then the difference between the force is almost 100%, right? You are designing confined masonry for 100 kilonewton, and for the same building, if you are going for unreinforced masonry without horizontal RC seismic band, you have to design for 200 kilonewton, right? So this is you have to understand, right? A flat slab system, we are knowing the flat slab. The flat slab is having higher depth of the, or higher thickness of the slab you have, and therefore mass of the flat slab is higher. We are knowing what is earthquake force. Earthquake force is mass into acceleration. So mass is higher, it means earthquake force is higher, and therefore the R factor is given is less here, right? So this is very important for us, right? So again, I'm saying that we are not designing for the 100% force, we are designing for the 20% force. We rely on highly on ductility, redundancy, and overstrength, right? So you have to be very careful that this feature should be there in your structure, right? Now the this R factor is completed, and then the next part is what? It is the basically SA by G. SA by G. What is SA by G? It is a spectral acceleration. Spectral acceleration means the highest value of acceleration observed, which is normalized with respect to gravitational acceleration, right? Now we are going for the SA by G value, right? SA by G. Now this SA by G value in the code, it is given this graph, right? This is the SA by G versus natural period. This curve is given, right? Now this natural period of what? It is a natural period of structure, right? Natural period of the structure. There are 3 curves given. For type 1 is a rock, type 2 medium soil, and type 3 is a soft soil, right? So the inner one is a type 1, then outer one is a type 3. It's a soft soil. Soft soil is having an enhanced response, right? Now this is we are using for equivalent static method. This is for the equivalent static method. The code has given 2 curves, one for the response spectra also, one for the response spectra, right? Now here, what is the difference? Here you can see it is 2.5 times, right? Directly, if your structure falls in this category, right, in this category, then if you have an acceleration, remember, if your structure is like this, right, and the natural period of a structure is less than 0.4 second, then your the slab will observe how much? 2.5 times acceleration. How much? 2.5 times acceleration, right? So 2.5 times, this is the one which is the peak ground acceleration, and your response is enhanced 2.5 times, right? So just imagine if the natural period of the building is less than 0.4 second, and here if I'm taking the example of Bhuj earthquake. In Bhuj earthquake, we have an acceleration of 0.6 g. So 0.6 g was the peak ground acceleration, and 0.6 g, remember, 0.6 g was the acceleration observed, multiplied by 2.5, right? If a building falls in a category having the natural period less than 0.4 second, right? So how much force is acting on your structure? It is 1.5 g. Remember, 1.5 g means the weight of the building is 1 g, and 1 g means, suppose the total weight of a building is 1000 kilonewton, for example, right? Then 1500 kilonewton load is acting in horizontal direction. Now imagine how much load is acting in horizontal direction. Is your structure is comfortable to this? No, your structure is not comfortable, I tell you. So this is the huge force which is acting in the lateral direction, right? So if the natural period of the building is less, then it attracts the higher earthquake force, I tell you, and that is dangerous. If we are talking about response spectrum method, right, then again there are three curves, but here 0 to 0.1 second, 0 to 0.1 second, there is an increased response, and this is 0.4 second, right? So this is given in the code, right? So here these values are already given in form of an equation also. Suppose if you are going for the equivalent static method, then we have to look at what is the natural period, right? The natural period is 0 to 0.4 second, then value of SA by G is 2.5. It is 0.4 second to 4 second, it is 1 by T, and if it is greater than 4 second, it is 0.25. So these values are already given in the code, right? So you can directly use these equations for the different types of soil: hard, rocky, medium soil, soft soil, right? And the same way for the response spectrum, right? Now what you need, how can you get this SA by Z? So what you need is a natural period of the building. What is the natural period of the building? Now how can you find out natural period? So the equation is given in the code. The equation is given in the code that if it is a bare moment resisting frame without masonry infills, then natural period can be counted like this: 0.075 H raised to 0.75, right? Same way RC steel, the composite or steel frame. This is for the building with the RC structural wall, and for all other buildings, all other buildings means buildings with the infill walls, then you can consider T is equal to 0.09 H by root D. H is the height and D is the base dimension. D is the base dimension in the direction of the earthquake, which is very important, right? So this is now clear that we are calculating the base shear, right? We are calculating the base shear first. Which equation we are using? The equation we are using is this: VB is equal to Z by 2 I by R SA by V into W S, seismic weight, right? We are using this equation. We are knowing VB. Once we know the VB, we have to calculate the forces acting, lateral forces acting at the floor level: Q1, Q2, Q3, Q4, right? So the distribution what we are assuming is a parabolic distribution. Remember, the parabolic distribution we have assumed, it is assumed by the code. So it's VB into WHI square upon WHI square, sigma WHI square. So design lateral force can be calculated, right? We are assuming that no imposed load on the terrace, only dead load will be there. We also say that 25% live load, 25% of the imposed load is considered in the seismic weight if the live load intensity is less than 3 km square. If it is more than 3 km square, we assume 50% live load, right? So the seismic weight is full dead load plus appropriate imposed load, right? So we are saying that here the seismic weight of the whole building which is acting, and the height what we are calculating is h1, h2, h3 like this. This is h1, this is h2, right? This is h3, height of the floor number 1. H2 means height of the floor 2, h3 height of the floor 3, h4 height of the floor 4th floor, right? So we have the height, right, and we have this equation, and we can calculate the seismic weight of the any floor, and this is the diagram we can plot, right? So this is the lateral force is acting on it, right? Lateral force is acting on it, and which is a cumulative, right? So maximum shear means lateral force is acting at the base, so it's a base shear, and this base shear is a cumulative of all the floors above it, right? So now we go for the very simple example. Example on from the Indian Seismic Code IS 1893. I had taken from IIT Kanpur and GSDMA EQ21 version 2. Right, I had taken. It's a this is the data we have. Consider a 4-story reinforced concrete office building. Remember, 4-story reinforced concrete office building is located in Shillong. Shillong means it is in zone 5. Generally, this data is not given, but you have to find out from the code in which zone this city is lying. The soil conditions are medium stiff, right? The soil conditions are given. The entire building is supported on rough foundation. The RC frames are filled with the brick masonry. So infill walls are there. RC frame is there. Infill walls are there. So lumped weight due to the dead load is 12 kg per meter square on the floor and 10 kg per meter square on the roof. The floors are to cater for a live load of 4 kg per square on the floor, 1.5 km square on the roof. Determine the design seismic load as per the code, right? So this is the plan. This is the plan, right? There are the 4 bays at 5 meter, and there are the 3 bays at 5 meter, right? This is the elevation. They're having the height 3.2 meter of the above story, and ground floor is having 4.2 meter, right? So here we have to go for the different zone factors, right? So zone factor, because the Shillong is in zone 5, so Z is equal to 0.36. It is office building, so we assume that it is not important. So we can add on that occupancy is less than 200, and it is not important. So we consider I value is 1. And we say that we are designing a moment resisting frame, so therefore R is equal to 5, right? So these are the values we are assuming, right? How you design. Now we are knowing that what is the floor area. The floor area is 15 meter by 20 meter, right? That is the floor area. So calculate the floor area. We know the live load, right? Now live load intensity is 4 kN per meter square, right? So the floors are W1, W2, W3 is having 4200 kN, and roof there is no live load, so it will be 3000 kN, right? So this is the loads we will calculate. So again, I'm saying here we assume 50% load, 50% live load. Remember, this is very important. full dead load. This is full dead load, but 50% live load. So we have a floor loads, and the total seismic weight is 15,600 kilonewton. Right now, the fundamental period. Now we are knowing that the brick masonry is there, infill wall, right? Infill wall is there, so we have to use the equation 0.09 h by root d. H is the height. What is the height? The total height is almost 13.8 meter, right? And the dimension in x direction is 20 meter, right? So you can see what is the natural period. The natural period is 0.28 second. 0.28 second is less than 0.4. Is less than 0.4. It means SA by G value is, what is SA by G value? The SA by G value, the graph is 2.5 SA by G. So now everything we have, Z is 0.36, I is 1, 2 upon R is 5 into 2.5. That is the SA by G value. So your value of AH will be 0.09H. And what is the design shear? AH into W, 0.09 into the seismic weight. So this is the base shear, 1440, right? 1440, there is a base shear, right? And now we are distributing W. This is the WI. This is the HI. So WHI square, and we are distributing at WHI square upon sigma WHI square, right? So we are knowing the weight of each floor. We are knowing the height. So it is very simple calculation, and we can calculate the total load which is acting. Base shear is 1440, right? So this is the distribution, right? So you can see this is the loads acting on your system. It's a 4-story building. These are the forces acting. I will share this example with you. You can refer this example, and it is very easy. And I think this part is easy. And okay, now we go for the second direction, Y direction. When we talk about Y direction, which Y direction we are talking about? Remember, this is X direction. This is X direction, right? So we have taken a 20 meter. Now in Y direction, it will be 15 meter, right? Value of D. Value of D is 15 meter, right? So we are taking this again H by root D. D we are taking, instead of 20, it is 15. Now again natural period is 0.32. 0.32 means again it is less than 0.4. So SA by G is 2.5. So the AH is 0.09. It is same as what is we have in X direction. It is the same in the Y direction. So the same distribution we have, right? So this is how we are doing this, right? So I think it will be very clear. Any question in this? Any question in this? Please, you can ask. If you have any question, you can ask, please. Okay. Now we go for the next part. That is the, yes, please. Yeah. Yeah. Any question? No question. Okay. You see, now we go to the second part. That is the dynamic analysis, right? Now, as far as the code is concerned, code has suggested two things: response spectrum method and a time history method, right? Time history method, we are applying the real time history of the earthquake, is a acceleration versus time. And the response spectrum, basically it is what we have earlier discussed, like it's a 3-degree of freedom system, and we have a different modes, right? And we are applying those modes here. So as far as the code is concerned, the code has described the complete method, right? So here you can see the code has given the method of the response spectra, right? So this is the dynamic analysis of the building, and we have to calculate the modal mass, right? Modal mass. You see, first of all, you have to. This is Wi phi. Now phi is the mode shape, right? Phi is the mode shape coefficient at the floor I, right? Everything we are knowing, but this mode shape, first of all, we have to derive the mode shape, and once we derive the mode shape, we can calculate the modal mass. Then what is the mass participating? For example, if you want to know that, okay, what is the mass participated? So that can be done here. Here it is a mode participation factor, right? Again, you must know the mode shape. If you know the mode shape, then again this is a simple calculation. So up to the mode shape, the dynamics is involved, and later on this is the process you have to follow, right? The same way you have to calculate the design lateral force, right? This is the design lateral force, right? So this is design lateral force you have to calculate, and summation of this design lateral force, summation of this design lateral force will be give you the base shear, right? That will give you the base shear, right? So this is the process you have to follow. So only thing is that you must know the mode shape. Once you know the mode shape, we can go for the calculation, right? So here we'll see that what we do in the response spectra. Now, what is the response spectra? The response spectra means this is the maximum response observed, right? We are catching that response, right? So if we are going for the maximum response, then definitely your structure remains safe for if you design for that response, right? So we'll discuss this part later on, but the main thing is that the important thing is the modal mass. Remember, this modal mass, 90% should participate. 90%, right? 90% of total seismic mass should participate in this modes, right? Now, if the frequency, natural frequency is more than 33 hertz, natural frequency is more than 33 hertz, right? Then we are taking the modal combination up to 33 hertz only. Remember, 33 hertz only. Okay, and the effect of higher mode shall be included by applying the missing mass correction. So these are the three things very important, right? When we are talking about the tall buildings, the higher mode, I told you higher mode may be significant, because the lowest frequency is the fundamental frequency, and in case of tall structures, the higher mode, a higher, right? So that is that we have to count, right? So you see, it is, what is the frequency? It's square root of k by m, right? K by m. Now the high-rise building is basically high-rise building is having very low frequency, right? Very low frequency, right? So here these are the things that I think comes with the experience. But here the important thing is this, and if a base shear, this base shear, what we are taking from the dynamic analysis, right? Base shear obtained from the is less than the base shear obtained from the static analysis, then we have to apply this multiplication factor to the values what we are getting to the the results we are getting for the dynamic analysis, right? So that is very important. We have a mode superposition or absolute summation method, right? We have different modes, and if these modes are closely spaced means the frequency, it is in a range of less than 10%, less than 10% variation in the frequency, then we can use this combination, right? So absolute summation can be done as far as mode is concerned. And if they are not closely spaced, we are going for the SRSS, square root of sum of squares, right, for the mode combination. And this is a complete quadratic combination which can be applied to anyone, right? Now this is the example. Again, here the natural period is given. Right? And the mode shapes are also given. These are the mode shapes. This is the mode 1. This is the mode 2. And this is the mode 3. The same example we are taking. Remember what we are considered for the static coefficient. The same example is taken here, but we are going for the dynamic analysis, right? So here we are performing the dynamic analysis, right? Dynamic analysis. Now these values are given right now. I'm not discussing that part. Basically, it is an eigenvalue problem we have to solve, and we must have these values. Then we can go ahead with the dynamic analysis or response spectrum analysis. Right? Now, again, the process is simple. That this is the modal mass. We have to consider, right? This is the equation. So mode 1, 2, 3 we are knowing, and we have to. This is the equation we have for the modal mass, right? So we have to calculate the modal mass. This is the modal mass for the mode 1. This is for the mode 2. This is for the mode 3. Right? So total, if you consider total mass, then 90% mass is participating in the first mode. And code is saying that more than 90%, it's okay. 90% mass has to participate. So if you consider the first mode, that will be okay. There is no need to consider the second and third mode, right? You get my point. So in the first mode itself, we are getting 90% participation. And generally, the first mode, most of the time, we are getting the highest mass participation in case of a regular structure. If it is irregular structure, sometimes a torsion mode may be dominating. This happens in case of irregular structure. But here, our structure is a very regular structure, 15 meter by 20 meter in a plan, and it is a symmetrical, so there is no eccentricity. So this is what we have, right? And then we calculate this value, right? Calculate this value, the value of Q means the lateral force which is acting at the floor level, right? So for the mode 1, we are calculating same way. For the mode 2, we are calculating mode 3, mode 4, right? So we can have these values, and on that basis we are calculating the shear, right? So we are knowing what is V1, V2, V3, V4, right? This is for the 3 different modes, right? 3 different modes, and we are getting the answer this, right? So lateral force we are getting, right? So this is the lateral force which is acting at the each level, right? Now you see what response we are getting. The response what we are getting here is basically 610, right? This is very important. This is 610, and what we have achieved in the static coefficient is it is 1400, right? It was 1400. So this divided by 610, so it comes out to be 2.3. So we have to scale up all the values by this value. So we are scaling up what we are getting the lateral force. These are scaled up, right? And once the scaling is done, then we can compare now. Look at this. This is the final summary. This is the final summary. This is the static. This is the dynamic. It is a scale one, right? Now look at this. This is 611. Here you get 389, right? 504, 404, 297, 297, 79, 214, right? Now, if you talk about the storage here, then look at this value. The storage here is 1491 in static, and in dynamics you get 1304, right? So in comparison of this, you see, actually we have scaled up the values of dynamic, right? These are the scale up value, right? Scale up value of how much? 2.3 times. If 2.3 you put here, it comes out to be almost 600, right? So 2.3 times it is scaled up, and it coming very close. So these two are close, but always static part is higher than the dynamic one, right? So here we get the answer, right? So this is the so I think for this dynamic analysis, you have to follow the process, right? That is important. You have to understand, first of all, mode shape. Once you understand the mode shape, it will be very easy for us to just if we make a program in Excel, we can do this, right? But the mode shape we have to find out. The missing mass correction. We are saying that at least 90% mass should participate, right? 90% mass. So total the mass participation is more than 90%. And sometimes what happen in case of structure with the basement, then the lower portion we have the shear walls or the diaphragm walls, and it will become too stiff, right? So what we assume that it will vibrate from the top only, right? So this mass is not considered at all. This mass is missing, right? So basically the top portion is considered, and when we analyze, for the first time we consider only this much, and the lower mass is missing. This is missing. So we are taking this missing mass under consideration, and then we apply the PGA and we analyze, right? So that is not the missing mass correction, right? So that's all. So this is what we have discussed. Now, if you have any question regarding this, you can ask. Now this is little means if you perform or if you do the calculation, then it will give you confidence, I tell you, right? If you don't perform calculation, then it is very difficult to get the confidence, I tell you, right? I'm sharing this example with you, so you can go through that part, right? If you have any questions, you can ask this. Hello, am I audible?
Yes, sir. You are absolutely audible.
Yes, sir.
It is, you see, again, I'm saying the static coefficient method is very easy, but when we go for the dynamic analysis using the response spectrum, you have to be careful. You have to understand the basics of dynamics. Means you must learn the mode shapes. Once you understand the deformed shape of the structure corresponding to the particular frequency, then it will be very easy for you. I have shared the example of this with you. You can go through this part. It is, I tell you, it's a good enough. Right. Now, if you have any question, you can ask, please. This is the example which is taken from the explanatory example, which is developed by IIT Kanpur and GSDMA, right? So you can go through that part. Now, if you have any question, please, you can ask. Any question? I think this considerably a very heavy dose. Dynamics is a little difficult to understand. Aditya?
Yes, sir. Yes, sir. I guess there are no questions as of now from the participants. And if at all you have any query, as we keep on repetitively saying this, you can also contact our experts on the WhatsApp group or the email ID. So I think we can culminate for today's session, sir.
Yes.
Okay. So that's all we had from our day 3 sessions. Thank you, Svetlana Brizev ma'am. Thank you, Major Dr. C.S. Sanghvi sir, for your wonderful explanatory sessions, quite informative and very exquisitely explain the details of calculations, the design part. Once again, all the participants, different references, IS codes, as well as the assignments and the PPTs and PDFs have been shared on the WhatsApp group. So you are requested to keep yourself posted and updated and keep yourself abide by all the resources which have been shared on the WhatsApp group. We will be continuing this STTP tomorrow. Tomorrow we will be having 3 speakers again. A renowned name in the discipline of earthquake engineering, Dr. Juan Jose Perez Gavidian will be joining us. We'll be having another session from Dr. Svetlana Brizev and Professor C.D. Patel sir. I guarantee there will be quite fascinating stuff to discuss tomorrow. So this will be all for today's session. Have a nice day. Thank you. Thank you very much all. Yes, the link will be shared to you tomorrow in the WhatsApp group. And regarding the timings and any update will be given in the WhatsApp group itself. So just keep yourself updated. Thank you all.